but still.
Oh, is there? No, not.
Raktim called me. He said he might be 5 minutes late because his laptop was not responding correctly, so he will log in from the other computer.
And what is the batting order? Who is going to bat first? You or him?
Raktim.
Oh, okay.
Raktim. And then
Hi, Mark. How are you doing?
Hi, good. I'm actually in the office right now.
Oh, I like your office with the bike and everything.
Well, the other picture I've had is of the Valle Caldera up there close to Los Alamos. I was getting a hard time. People were complaining I was working outside.
I see.
Yeah.
I think Aichiro is there also.
Nani?
Yeah.
One.
Hi. So let's just wait a few minutes. So Mark, the equation learner program that you have, right? That's the last version. You tested it, right? You ran it.
Yeah. So we ran it on some of the examples in the paper.
But you also ran on some polymer problem, right?
No, I have not.
Okay. You just checked some of the things in the paper.
Right. Yeah. No, I've been talking with Thomas about doing some other things.
Okay.
But
and you know, I also ran it, and so Anikya was saying that he tried to run it and he ran into some difficulties, okay, which I will clarify with him. But Anikya, I just wanted to let you know, Mark and I have run the program independently.
Okay.
Yeah, so it works. So Nitish is there.
Raktim is here now.
Okay. Okay. So, you know, the thing is, I mean, last week I talked.
Hi, Rajiv. Sorry.
And Ikea. And
can you hear me?
So,
Professor, your audio is breaking.
Yeah, we can hear you. Yeah. So Raktim, why don't you show your screen, okay, and then you can start your presentation, and Anikya will follow you.
Yeah,
and
no,
I think they are.
Yeah, so yeah, I can start. We plan that Anikya is going to share the screen because he has the combined slides. So I will go first, and then he will follow. Yes.
Okay, yeah, just give me a moment.
And they are working on two kinds of problems, which are both very interesting. Okay.
Yes. So Anika, if you can go to slideshow, yes. So yes, so Rajiv, Anika, and I, we have been discussing a lot of ideas. I mean, with the group. So we have actually started.
Just 1 minute, Raktim. Anikya, can you remove the right-hand side all these slides so that we can see the full screen?
I already did. Wait, it's not working. Let me redo it. Just give me a second. I will first remove the floating control panel. This gets in the way.
Very good. Okay, yeah. And just project it.
This one, wait, still goes back. Wait, why is it doing this?
It's okay. It's fine. We can see the screen. Let's just go. Okay.
Yeah, let's just. No, it's not working. Yeah,
no,
just stay like this.
Yeah, that's okay.
Okay.
Yeah. Okay. You.
So yeah, Ruptam, you can start.
So yeah, I mean, Rajiv, Anika, and I, we meet basically every week and we discuss with the group. So there are, of course, a lot of ideas that are going around. So we actually have started working on 2 ideas to get us started. And these 2 ideas are basically studying light matter interaction at the, at the nanoscale. And we want to use, I've used the word artificial intelligence, but it's basically, we want to use components of machine learning to be able to optimize a certain response as well as be able to inverse design. And I will show you examples of these two problems that we are working with. So Anika, if you can go to slide 2. So there are essentially 2 problems we are working on. The first one is a meta surface. So I'm just showing you a schematic of what a meta surface is. So meta surface is usually an array of subwavelength size and spaced resonators. Now, these resonators can be of different material. It can be metallic, in which case you call them as plasmonic meta surfaces, or they can be dielectric. For example, in this particular problem that we are studying, these are made out of this perovskite material that Joy can grow, or it can be just silicon or any other semiconductor. And by controlling the shape, size, as well as the periodicity and spacing of these resonators, you can usually acquire different optical responses. So one problem that we have started is concentrating on this meta surface. The second one is, which everyone else here is an expert on, is essentially 2D materials. And we are specifically, instead of looking at pristine 2D materials, we are looking at alloys. And Anika will go into more details later on. So let me first start on the meta surface. I mean, since many of you may not be familiar, I'm just going to go over a brief introduction on what a meta surface is and what kind of modes we are specifically concentrating on. So if we go to slide 3, so just like I was saying, is that if you look at the figure on the left, it's a schematic, and the idea is that if you have a conventional material system, if you want to change the light matter interaction, and which is the goal of this project, is to study light matter interaction at nanoscale, you have to change the atoms and molecules, or you have to change the chemistry. Now, metamaterial are essentially subwavelength, are an array of subwavelength size and space resonators, and they give you a resonant response. And by controlling the shape and size, you can tune this resonant response, and which allows you to have optical responses which you do not see in nature. Now, of course, metamaterial, usually when you talk about metamaterial, it's a 3-dimensional object, which are very hard to fabricate. So recently, meta surfaces, which are planar structures, are gaining more interest because they are easy to fabricate. Now, in terms of meta surfaces, just like I was saying, you can have plasmonic meta surfaces where you use the plasmonic resonance to tune your optical response, and you can have a dielectric meta surface. In the particular material system that we are studying, which is the perovskite, it is more like a dielectric. So I'll be talking about the dielectric meta surface here. So I think if you go to slide 4. So dielectric metasurface, there can be 2 types of dielectric metasurfaces. The first one, which people study, are basically very tall structures. And these tall structures are, so when I say tall, they are much taller compared to the wavelength. So they are like waveguides, so they can guide light. Now, the second type of structures are actually comparable to the size of the wavelength. Now, if you have a particle, a dielectric particle, based on that size compared to the wavelength divided by refractive index, you can have different type of responses. For example, if that particle is much smaller than the wavelength, which is what I'm trying to show on the figure on the left, you have a phenomenon which is called Rayleigh scattering. It is the scattering strength is inversely proportional to your wavelength, and it is why, for example, the sky looks blue. Now, when you make this size of these particles bigger, and this particle basically become comparable to the size of the wavelength, these particles, when the light is incident on this particle, they can actually trap the light, and they support resonant modes. And these modes are called as mean modes because they look like mean modes in a spherical particle. And essentially, you can have an infinite number of modes. And if you look at the first 2 orders mode, so basically the lowest order modes, the first one actually looks like a magnetic dipole. And what I mean by that is that if you actually look at the electric field component inside the resonator, and that is what I'm trying to show as the inset in that figure, it has a circulating electric field. So it looks like a magnetic dipole. And the second one looks like an electric dipole. So it has a circulating magnetic field. Now, in Jaikan's project, this magnetic dipole actually, and I'll show you later, is kind of crucial. The fact that you have a circulating electric field actually will allow you to achieve certain abilities that you do not get if you just have a plain slab with an incident plane wave. But these are the modes that in this particular metasurface project that we want to play with. We want to optimize these modes to optimize our light matter interaction. So if you go to slide 5, Anik. So these Me modes in dielectric metasurfaces have been used for many different applications. So there's, in broadly speaking, they're mostly studied for linear and nonlinear optics. So when I say linear, what I mean by that, you make the structures and then you shine light, and the metasurface is going to change your reflectance. It's going to change your phase, as well as let's say absorption, or your how that structure behaves for different polarization. So these are the linear properties, and that's what we are focusing here, linear. When I say nonlinear, essentially what you can do is that you can make these metasurfaces out of materials which has strong nonlinearity. And actually 2D materials are being investigated for that because they have a very high second order nonlinearity, and you can use this to generate harmonics or nonlinear signal. Basically, you can do second harmonic generation, so and so forth. So in this case, we'll be doing only linear optics. So, and the one that we're focusing is basically reflectance. So if you go to slide 6, so the material that we are investigating is essentially barium titanium sulfide, and Jaikan gave a very nice talk about that of his material. So the basic idea here is that this material, based on the axis, and this is what, so the figure on the top right is his experimental data. So you have the C-axis, which is essentially Z, and if you are in plane or if you're out of plane, as light propagates through this structure, it sees different refractive indices. Now, because it sees different refractive indices, when you look at the reflectance, which is the linear optical response, you see different reflectance. So for example, here actually in the figure, the labels are mislabeled. It should be flipped. But if you look at these two orange and green curve, you can see that one has a higher reflectance and one has a lower reflectance. It's because it is, as light is propagating on these two different directions, it is seeing these two refractive indices. Now, the first thing, what we have done till now is that we actually got the optical constants of these material from the paper with help of Jaikan, and we tried to see if we could first reproduce this paper, the result of this paper. And what you see below on the bottom right is essentially an finite difference, FDD simulation of the structure. So we didn't simulate the entire wavelength. We only simulated up to 8 just to save us time, computation time. And you can see we see a fairly good agreement. You can see these fringes, and these fringes are coming from the fact that the crystal is about 12.7 microns thick. So you have what I call Fabry-Perot fringes. And also the magnitude, which is more important, kind of, they match relatively well. We see a slight, for the green one, we see slightly small number as what is seen experimentally, but that is probably because in the experiment, instead of coming with a plane wave, he used an objective, so it has a few angles there. And actually angle, just from Fresnel's law, you have different reflectance when you're coming from normal incidence or different angles. And in the simulation, we use pure plane waves. But in general, I think this was the first thing we tried to make sure is that whether we have the framework, and it seems that we can match experimental results pretty well. So we have now the framework ready to do more calculations. So now that we have that, so I will essentially I'll discuss what we are trying to do. So if you go to slide 7, so here, we don't have results yet, but I'll just explain what we are trying to do with these kind of material systems. So let's say, so what Jaikan is trying to do now is to be able to grow these kind of material in a lower index substrate, so around 2. Now, when you do that, you can, let's say if you can fabricate cylinders out of this structure. Now, the way you can see this anisotropy in a slab is dependent on the polarization of your electric field. Like I was saying that you have the anisotropy, whether you are in plane or out of plane. So let's say if you are coming from the top, which is what I'm trying to show as a schematic on the left, you have the K vector, which is the incident direction, and you are coming and your, let's say your electric field, which is E, is polarized along X direction. Now, if you want to see this anisotropy, so the way you have to do it is either you have to flip the structure, you have to rotate it by 90 degrees, or you have to come at an, from the side, which is the next figure, center figure, where you can see that the K is coming from the side. Because when you do that, now in one case, the electric field is polarized along X and Y in plane, and the other case it's along Z. But if you think about an experiment, usually that's not a very convenient thing. So what we are trying to do here is that we are trying to design a matter surface such that you can come with normal incidence. So the figure on the left, but you can kind of, but we designed a structure such that the light sees the anisotropy. And the way we are trying to do this is essentially trying to use the me mode that I had explained before. Now in the me mode, like I was saying, if you are working with the magnetic dipole mode, the magnetic dipole mode has a circulating electric field. And the figure here on the right essentially is a field plot of the structure in using Jaykan's material. And the vector here are showing the pointing vector. And you can see it's circulating. What that means is that this is in the XZ plane. What it means is that there are, even if you're coming from normal incidence, the fact that this cylinder can support modes, you have modes which have strong out of plane or Z component. Now, because that means that the electric field, there are electric fields that are polarized out of plane, which means that even if you're coming from normal incidence, you can actually experience this anisotropy. Now, this anisotropy that you see, if you use a cylinder which is symmetric along X and Y, whether your electric field is polarized along X or on Y, it doesn't matter because the light basically sees the same structure. Now, along with this mode, if you start breaking the in-plane symmetry, let's say if you go from a cylindric, like a circular cross section to an elliptical cross section, you can break the in-plane symmetry. So you can design your structure such that in one case, let's say along X polarized, you can support this magnetic dipole mode, or in the other case, which is along Y direction, it does not support the magnetic dipole mode. And when you have that, you can actually see difference in the X and Y polarization using the anisotropy that's in the Z direction. And so, of course, this would depend on the geometry of the structure. If we fix the normal incident direction, and that is exactly where machine learning comes in. So what we are trying to do now is that since we have the framework, we are running simulations of different structures, and the idea is that we want to do a shape optimization such that we see the maximum anisotropy. And the way we want to quantify that is by looking at the linear optical reflection. So we want to see the reflection. We want to see how much the reflection changes when you change the shape by such that the different shape support different modes with different field distribution. And then we want to do two things. One is we want to use the joint method, which Anika is going to go over more details to do shape optimization or an inverse design. And also we want to do the equation learner so that we can have some sort of an analytical expression that can determine how this reflectance changes as a function of shape, for example. So these are the two ideas we have of using machine learning in this kind of structure. So any questions in this part?
Yeah, Rakim. So how are you going to be changing the shape? Is it going to be a cylinder or what?
We are exploring. I mean, this is something we're still discussing, but it doesn't have to be shape. We can define a grid. And in reality, we don't want any in-plane symmetry. So let's say we can define the cross-section area to be 1 micron. We can make it a grid. It can be a rectangular grid. Some of these regions are going to have this medium. Some of them won't. So so basically, let's say blue and white is air, right? So we can design that way, or we can have contiguous shapes, for example, circles, ellipses, squares, so on and so forth.
And Mark, as Raktim was saying in the beginning, we can also break the symmetry by randomly removing some of these cylinders.
Mm-hmm.
Okay. So that's like introducing, point defects in a crystal.
Yeah.
So
yeah, go ahead. Yes.
So you're computing reflectance, But you're using the time domain that finite.
Yes. Yes.
So why do you use a time domain to get the reflectance?
So when you do a
That's
time
a steady state, right? Kind of
Yeah, but
reflectance calculation.
yeah, but Aichiro, the equations, Maxwell's equations are time dependent, right?
Yeah, but I mean the scattering problem, we don't usually do a time domain.
True, but we still have to solve Maxwell's equations to get, electric and magnetic fields, right?
No, it's like a boundary condition, like a plane wave, like in quantum mechanics, we don't do
No,
time
you are
propagation
absolutely right.
scattering
Yeah.
problem.
So you what you're saying, you can do harmonic analysis and then it becomes an eigenvalue problem.
Yeah, so yeah, that's my question. So
Okay, Raktim knows the answer.
Why time domain is better?
So when you do harmonic, yeah, you're right. You can do, I think the question in the optical analog would be, why don't you do frequency domain? I mean, the advantages of doing the time domain is you get a broadband frequency response. So if you look at the reflectance, let's go to, Anika, if you go to slide 6. If you look at the experimental data, you have reflectance as a function of wavelength, which is a typical experiment. Now, if you do anything in frequency domain, you have to compute all these frequencies.
Right.
Now, what FDDT allows you to do is, because it's time domain, you define your pulse, and then you just do a Fourier transform. You get the information of all the frequencies at once.
Oh, in one go. Yeah,
in one go.
That makes sense. Okay, thank you.
And I think for at least, I mean, we have many ideas. Some of them, like you said, we may even end up doing frequency domain. But as of now, since we are concentrating on linear optical responses, which are usually frequency dependent, I think FDDT would be a right way of approaching it.
Yeah. But what Aichiro is saying is absolutely right, because I mean, it can be cast as an eigenvalue problem, just like time independent Schrodinger equation.
Yes, you can take this problem, you can get the eigenmodes of the Maxwell equation. So that's exactly what a finite element method does, frequency dependent. So it's called a COMSOL. There is a commercial software there, which they do. But like I said, you have to then compute all the frequencies.
Right.
So you don't get the broadband, optical response. Yeah. Which I guess for this particular problem we're trying to do can be helpful.
Yeah.
So this is something exploring. Like I said, we wanted to show you that we are doing stuff. We don't have the results yet. So Anikya, Rajiv, and we are working on designing these structures. But I think that at least for this JICON structure, the physics seem to be correct. I mean, it should work. And one of the reason is because I have worked with systems where I embedded quantum wells inside cylinders. And this quantum wells, if you are in the conduction band, if it's an inter-subband transition, the selection rule allows you to couple only to Z polarized light. And the way I could do it is actually using one of these Mie modes while coming at normal incidence. So by that logic, I think this should definitely work. And if we can do something with adjoint or equation learner, I don't think, at least if we can do equation learner, I think that'll be very new, because no one has done something in a photonics using that. And especially since equation learner, I mean, I think Anika is going to cover some details, will allow you to extrapolate. So all the work that I've seen in photonics has been optimization and interpolation. So equation learner, if it allows us to extrapolate, let's say the reflectance dependence, it can extrapolate. I think that can be pretty significant piece of work.
Yeah, and Aichiro, Mark, I mean, everybody, the intent here for making this joint presentation between Raktim and Anikya is to get your input, okay? So that, I mean, useful suggestions can come right at the beginning of a project, which can be incorporated.
Yeah.
So that's one type of problem. And the second one, which Anika would go in more details, but I want to show you some initial results, is essentially working on 2D materials. So what we have done, Anika, if you go to slide 8, so what we are trying to do now is to develop a FDDT framework so that we can simulate these 2D materials such as MOS2 or WS2. So what we have been able to do now is that there is this very nice paper from Heinz, which is one of the most cited paper. It has all these optical constants, and they actually measured the linear optical response. And that's what is shown on the left in the figure. So they measured the reflectance, and again, they measured, I mean, this is photon energy, but you can convert it to wavelength. So again, Ashiro, coming back to this, if you want to replicate, it's easier if you do time domain because you get the whole, the wavelength range information. So this is Heinz data on the left experiment. And what we have been able to do so far, I mean, the way he did this is that he exfoliated MOS2 or CVD grown MOS2. He has put it on a sapphire substrate and he measured the reflectance. So what we have been able to do is that, from the experimental constants that he has measured, optical constant, we have been able to reproduce his data. So on the right here is essentially an FDTD simulation of that structure. We try to replicate his structure, and you can see that we are getting a very good match, both in terms of the magnitude as well as the spectral dependence. So now this is where in this 2D stuff, this was like the first thing, just like we had in the JICANs, we wanted to first make sure we can replicate some experimental data. So now what we are trying to do is we are trying to simulate alloys. So instead of having a pristine MOS2 in this structure, we are trying to simulate what happens if you have an MOS2 with WS2, for example, either periodically, located or placed within that MOS2 or randomly. And that's something Anikya, I guess you can start now. He's going to go into more details on that.
Aichiro, and this alloy system is the one we worked before, remember?
Mm-hmm. Yeah.
Yeah, the one that, rights people, against people, synthesized.
Yeah.
So are there any particular challenges in dealing with the 2D material and doing the FTDT calculation?
So it's really, it is. I mean, the meshing is an issue. So you have to be careful with the meshing because, you're dealing with sub-nanometer, structures. Right. So the way, at least when I was reproducing this result way, is that I was doing a scan of different mesh sizes and trying to see the convergence. So that's definitely an issue. And I mean, but if you know and another thing is that because these are, like for example, JICAN's material, the N and K, the optical constants are very well behaved. They don't have some crazy features. But some of these 2D materials, I mean, at least WS2, I was working with Anikya last night on that. It has like, they have this exciton peaks and things like that. So they give these features. And if to be able to do these simulations, you essentially in Lumerical, the software, you do a fitting. So you take the data, you fit it with a model, and sometimes the fits are not good, and then you don't get, you get something, but that's not right. So that's another part.
Yeah, but Raktim, as we discussed, their neural networks will be very useful because I mean, you can do regression very well with neural networks.
Yes, and I think Anika is going to talk about that. Actually, we discussed. Yeah.
But Mark's question is very good because Mark, the one thing that we are struggling with, and if you and Aichiro and other people have any ideas, it will be very helpful. You see, we are interested in vertically stacked layers, right? So supposing you have a bilayer and you want to rotate one layer relative to the other one. How do you introduce the right kind of boundary conditions in that case? And that is something not clear to me. Okay, so
yeah, that's something actually. Yeah.
So if you guys have any idea.
Raktim?
Yes.
How do you handle these 2D materials in the simulation? The thickness of the layer.
So in this particular simulation, we actually went and looked at the paper, and they said the thickness is 0.615 nanometers. So
I see. Some effective thickness.
Yes, effective thickness.
Okay, I see. Okay.
Yeah. But that's actually a very, it's a very, very critical question because you kind of have to take it as an effective thickness. And, this is where I think experiments lead simulations in these kind of problems because you measure that experimentally and then you kind of tune your parameters to match it. That's why I think both I mean, Rajiv and I, we wanted to make sure that we can, before we do any other simulation, we want to make sure we kind of reproduce what's out there in the experiment.
Right.
Because otherwise we don't know, right? But it's right.
Yeah.
Yeah.
Okay. Good. Thank you.
Yeah.
So
And the
Rakeem,
other thing is, I mean, usually these things are on a substrate also.
Yes. Yes.
Usually alumina.
Yeah. So in this particular case, it was definitely alumina, and then we took that into account. And indeed, I mean, I ran simulations where I removed the substrate. You start seeing, you definitely start seeing differences.
so Rakeem, how small does your mesh get?
This is 0.1 nanometer.
Okay.
Along the, so because your crucial parameter is along the thickness, which is, let's say,
I can like probably give an example. So like,
okay. Yeah. So you see, along the X and Y, in this case, it was an infinite film. So, but along the Z is where you have the 0.615, and there the mesh was 0.1 nanometer. So you had about roughly, 6 mesh points per thickness. Yeah.
But the light doesn't see that.
Yeah, this is the strange thing, right? So when you deal with this effective NNK and effective thickness, if you do based on that, the wavelength, of course, is much longer, but you still see this reflectance, right?
Because of the interface, yeah.
Because of the interface, yes. So, Anika, do you want to now go more details about the methods and the alloy system?
yeah. So
maybe you can start with the alloy system because we are there, right? What we're trying to do, and then maybe talk about the.
Yeah, I think it can work. Yeah.
Yeah.
So the alloy system we are looking at is the MOS2 WS2 alloy, where the blue part is basically the MOS2 sheet, and in that we have embedded hexagonal shaped WS2 in an array form. And for us, for this size of sample, the dimensions were like 1300 nanometers in X and Y, and the thickness, as roughly mentioned above, we kept 0.615 nanometers. And each hexagon for WS2 has a phase length of 100 nanometers. And the way we are going to run the simulation is, for now, we have placed it on a glass substrate, but we can change it, and we will shine a plane wave source light in the Z direction and calculate the reflectance using the monitor here. So for now, because we only have the dielectric constant values for both MOS2 and WS2 from 400 nanometers to 800 nanometers. So our light source will also have wavelength of frequency in this range. And then from there, we will calculate the reflectance. And before, means I also wanted to like introduce a joint method and equation learner and show you how we plan to use it in the project.
And Anika, you should mention one thing, that is the system that you have constructed, by the way, with hexagons, WSC2 on MOS2. Yeah. Such systems can be synthesized these days.
Yes.
Experimentally, it can be done.
Right. Yeah.
And do you have data on this, the dielectric property of these two materials?
Yes. So we pulled it out from the. So the paper which had this plot, it also had plots for WS2, MOSC2, WSC2. So we extracted the data from there. That's why we are limited in this energy range, which corresponds to 400 nanometers to 800 nanometers.
Oh, okay. And then, so band gap of both materials are smaller than 1.5 electron volt.
I
guess
I haven't checked it.
Yeah.
It has to be light is passing, right?
Yeah. I know MOS2 is like a 1.3 electron volt or something. Yeah. So I was just wondering. Yeah. So you have data from 400 to 800 nanometer.
And also, Anika, I sent you this paper from Notre Dame, right? University of Notre Dame. They also have data for these materials.
Yeah, I think you have sent me like 3-4 papers which have some data. One has only one material and one has few materials.
Right. And these two materials are given in the paper from Notre Dame.
Yeah. But I have only pulled out data so far from the
Heinz
paper. Yeah. Okay, so first I will introduce the adjoint method. So the adjoint state method is a numerical method for efficiently computing the gradient of a function for a numerical optimization problem. So for example, if we have a function f, which could be a loss function or a merit function, and we want to optimize it, and then we also have constraints g, then we can use the adjoint method here. And I'll just give a example from aerodynamics to show how it works and why it's so much cheaper than using a brute force method. So for example,
why don't you give the example from electromagnetics?
I have that also here.
Okay, good. Okay,
I thought I'll use this to show, like, set up the adjoint.
Perfect,
and then,
perfect. Very good.
Yeah.
Go ahead.
So for in aerodynamics, we want to, let's optimize the shape of the wing so we can maximize the value of lift by drag. So our two parameters of interest are camber and angle of attack. So a camber is the asymmetry between the two facing surfaces of an airfoil or wing. And if the top surface has more convex, then we say it has a positive camber. And the angle of attack is basically the angle between the chord line of the wing and the direction in which the wind is facing the wing. And for this problem, we will have the flow variables, which are UW, V, and P, where U, V, and W are the velocity of the fluid in 3 directions, and P is the pressure. So for example, if we use the brute force way, the straightforward way, let's say we have 100 data points along the surface of the wing, and each data point has an X and a Y value. So we have a total of 200 parameters. So we start with the initial value, and then we use the flow equations to calculate, let's say, 10 million variables. It could be more or a little less. So we calculate the entire field around the wing. And then from there, we calculate lift and drag. And then if we have to change just one of these values a little bit, we change them, then we again calculate the entire flow variable, and again calculate lift and drag, and then see if it changes or not. And for 200 parameters, we have to do this 200 times to see if there is significant change or not. So this method could be very expensive. So we can make it cheaper by doing it reverse. So once we start with our initial set of parameters, we do one forward calculation, and we get the lift and the drag. And instead of redoing it, what we do is we find how the lift and drag change with the flow variables in the field. And from there, we find how the flow variables change with changing the X and Y by calculating their derivatives. So in one forward and one backward loop, we obtain the gradients for the entire space. And that's how it can make us, like, it makes it very cheap to perform gradient descent calculations. Now, I want to show like how we use this method as inverse design in electromagnetic problems. So in electromagnetics, in inverse design problem, what we aim for is, we say that we want a certain desired field values. And what we have to do is we have to find a geometry which can produce it. So, and the constraints for this problem are the Maxwell equations, because if there's a solution, they must satisfy the Maxwell equations. And the method they call for solving this problem is shape calculus, which helps us optimize the problem and solve it very fast. So let's imagine a very simple example where a wave is incident from top with transverse electric polarization, and the electric field is scalar everywhere, and the permittivity and permeability are also assumed to be scalars. And the objective function we want to maximize is given by this equation. So in the brute force method, we will start with initial geometry, and we will select an inclusion point where we'll change the dielectric value of the structure, and then calculate the electric field again, and then take the difference. And we will have to do it again and again for each point. then pick the best value and then repeat the process, which could be very time consuming. So to reduce this, we do two changes. First, we model the interaction between the electric field and the new dielectric inclusion based on a dipole moment. And then we use the symmetry of Green's function in Maxwell equations to transform the whole problem into just two simulations, where what we do is we consider the starting geometry and with only vacuum, and then we simulate the electric field for the entire structure. This gives us the potential induced polarization for all the possible inclusion values. And then we use that electric field to calculate the adjoint electric field for all possible inclusion points. And hence we can reduce a problem which will, let's say, take n+1 simulations into just two simulations to get the gradient value for one step. And that's how we can use this method to optimize our structures.
Yeah, Anike, this is very good. Do you have a reference on this electromagnetic field formulation?
Yes, I have. It's from a thesis, and means I skipped a lot of equations here. Because,
right. Yes.
Yeah.
I can see that. If you could share with with us that reference.
Yeah,
I can share it with you.
Right, this it comes from the thesis of a student. His name is Owen Miller. He was a student at Berkeley. And he was a student of Jablonowicz. Remember, USC tried to hire Jablonowicz at one time, but he went to Berkeley. He used to be at at UCLA.
Okay.
It's an excellent thesis. I mean, really, it's a pleasure to read it.
Yeah,
Okay.
it's very interesting.
Yeah. I can show the main equations right now. It's like I tried to make it into slide. But...
Actually, you can put in a chat.
Yeah.
Okay. Page I can download.
Raktim knows.
Okay, I will put it in chat after the presentation.
So he's a faculty at Yale now.
So that's how we will use the adjoint method to optimize our structure. And the other thing we want to use is the equation learner. So equation learner is basically a neural network that can learn analytical expressions and is able to extrapolate to unseen domains. So I'm just taking one example from that paper where they try to learn the equation of motions of a pendulum. So we first start with the known differential equations which govern the pendulum's motion. We then divide it by g just to balance the output. And then we use these two equations to, let's say, generate data points which we will use for training. And what they found is that they compared three algorithms or three ways: equation learner, multi-layer perceptrons, and support vector machines. And they found that, so the gray area in this plot is where the training was done, and the white area is where they tried to extrapolate it. So means apart from EQL, support vector machine was able to grab the extrapolation value for a near range. But as you can see, as we move far away from the training range, EQL is able to approximate the underlying function really well. And
Anika, sorry to interrupt. I have a quick question. So if you're not a periodic, I mean, I don't know much about this EQL, that's why I was asking. If you, and maybe Rajiv, you can also chime in. So if you don't have this kind of, I mean, it needs some sort of training data, right? So here, is there like an implicit assumption that this is going to be a periodic function?
No.
No, okay.
No, means there are other examples where it is not like that.
Okay, so.
But Raktim, one thing is very important, and this is something Mark and I discussed, okay, when we were working on it. You see, if you're working on a 2D problem, you know, in 2D, you can expand any function in terms of Legendre polynomials, correct?
Yes.
Because Legendre polynomials form a complete set. And Legendre polynomials consist of cosine and sine functions only.
Yes.
And powers. So this will work very well for 2D systems. Okay.
Okay. I see. So then this is great, right? Because let's say if you look at, you know, I mean, let's change this graph. Let's say it's a reflectance. right, as a function of frequency,
Mhm.
right? I mean, you can
You mean-
definitely extrapolate. Oh, yeah, something like this, right?
Uh-huh.
Yeah. Yeah. Okay. Yeah. Sorry to interrupt you.
Yeah,
Yeah.
no worries.
So this thing, I mean, equation learner, for example, you can give a certain range and ask equation learner to fit it and then say, okay, for wavelengths outside the range. And
Yes.
it will be a very good test.
Yes. Yes. I mean, and I mean, for the meta surface or the 2D material, I mean, we can test it right away, right? Because
Absolutely.
for reflectance, and we can see, and if we can show this, I think this is great, because in optics we are always limited by our detector wavelength.
Yeah.
So the fact that Heinz could only measure 400 to 800 is because that's what the detect. I'm sure either the laser or the source or the detector, right? So if you can do this, this is great for optics because you go beyond your hardware limitations.
Yeah, and moreover, FTTD simulations are expensive. So if you
Yes.
do the limited range and then you can, extrapolate, and if the extrapolation works, that saves a lot on computing.
Yes. Yes.
So we will try this. Yeah.
Yeah, and in the final, the equation learner predicted was these two. So if we compare this to the equation used to generate the data, you can see it's perfect match, except for here, 1 by G is 1.01 and the machine learning predicted 1.03.
Okay.
Yeah, and my idea was that we can use equation learner to probably see if we can find dielectric value in higher wavelength range. If we, let's say, only give this range of data as a training, can it predict this feature and this feature? But we can also try it on the reflectance plot as Raktin suggested.
Yeah.
But this will be your input in this case, right?
Yeah, so main example, like for this example, their input range was, let's say, only this.
Right.
And equation learner was able to predict this feature and then this feature. So if I give, let's say, from here to here, can it predict this feature?
Right.
Yeah, just to test.
It will be good to do that. Yes.
Yeah, and after that, I was gonna just talk about the alloy we are working on to run
But
simulations.
If you go back to the previous figure, one thing you can easily try, you can take any garden variety feed forward neural network and just fit this thing in the range that you're interested in, and that will give you a better fit, okay, than anything else, because you have this very sharp structure around 600.
Yeah.
Okay.
The interpolation algorithm from Scikit does perfectly fine. Like that's what I used to get the data for running the simulation here.
Okay, so you have already tried that and that works.
Yeah. But my idea was like, what if we want to run, let's say, more than 800 nanometer wavelength?
Absolutely.
Yeah.
Good to test.
And so, yeah, this I have already talked about the simulation structure. So I have already submitted one version of this simulation for running, but it's in the queue. So I think it'll be done by probably in coming days.
And then Aniki, you can also, in your structure, you have hexagons, right? If randomly you remove some, if you have a lot of hexagons, then you will produce a random configuration of these.
That's where we can use the adjoint method where we can see how the changing the hexagons affect the response.
Right.
Yeah.
So more questions for Aniki and Raktin? Any other suggestion for any other system? Okay. So if there are no more questions, I think very good. I mean, you guys are finished in 50 minutes. Okay.
Yeah.
So we will, yeah, you guys just keep everybody informed as, you get, more results.
Yeah, I will just put the thesis in the chat.
Right.
Thank you.
Yeah.
And also you can put experimental paper, Heinz's paper.
Oh yeah, those I have. I'll send it an email because those I have in other folders. I will have to like arrange them and send it.
Okay.
Yeah, but yeah, this one, the thesis.
Actually, I have it, so I can put it.
Okay.
This is the paper you're talking about.
Which one?
Yeah,
This the one, Lee.
yeah,
Isn't
this
it
one.
2014.
Yeah.
Yeah, this is the one, Aichiro. Yeah.
Yeah, this is the one where I got the data from.
So you have 4 material.
Yeah.
So you're going to use 4 material to run.
For now, we just extracted the data, but yeah, we have for now 4 options to change.
But Aichiro, as you can see, you know, for example, if you look at WSC2, the data, it looks very different from some of the other materials.
Yeah. But the thing is, this A and then B are common feature. It's what is this extend to 2 value or something like that.
Right.
And then after that, some of them has just 1 broad peak.
Right.
WSC2 have two.
Right.
Those are different.
Right. Okay, if there are no more questions, Anikya, thank you very much. Raktim, very, very good. Okay. And we will continue to discuss these things over the weekends when we have new results.
Yeah.
And you can share them with everybody.
Okay.
Yeah.
Okay.
Thank you very much, Anki and then Raktim.
Yeah, thank you.
Yeah, thank you.